just before we wanted to define dimension. And there's a little chart there. Topology, all these topics in topology are two things which almost started topology. One is what is meant by a curve, and the other one is what is meant by a dimension of a space. Dimension of a topology space. But we have no metric space. Metric spaces. So the dimension ought to be defined using distance. And that is the motivation for Professor Bloom. He's long time past, in 19, for him to write that monograph, where it is very rigorously. So we are now going to define a generalization of this concept, which is not published yet, but it is not too difficult, and it should be done this way. Before that, we would like to recall that if X is a metric space with a distance function distance function rho. BR subset. Then we can define distance between A and B. Rho A, B, B. Minimum of distances, which exists because the codomain is non-negative element. Y is in B. This is a distance between two sets. We do not assume they are disjoint, not equal, or doesn't intersect. No need to assume. And if one of them, one or both of them is a single element, let us just keep one. If A is a single element, we want to be lazy mathematicians, always want to do less and get more results, which is probably not true now, but now we are making too much effort to get just one paper published. But the mathematicians are known to be lazy, as much as even on typing on the computer, you don't want to type these two. That's why we are doing it. This is notation, we are abbreviating, and we're just dropping these two types. So if one of them is a single point, then we just use the set notation. Now we define the general metric dimension. Metric dimension is done by several dozens of people in Pakistan, from Pakistan. Some of them are now in Saudi Arabia. At least two I know are in Saudi Arabia. Too many papers have been published in ordinary metric dimension of finite and reactive singulars, and usually for a very special family, which is not very good idea, because of course you can quickly publish papers, but impact is very low. If you define, if you make the definition as general, like what I'm going to write, so this is a dimension, definition of a dimension. It is much better, and then nothing is done. I think I got 2 million pairs of brackets now. So let X be a metric space. Put this on function rho. And we take a subset of natural numbers. And assume that for every index from this subset, E sub I is a subset of the metric space. Metric space. We are taking, for an index set, we are taking subsets. You can say that it is a sequence of subsets. Actually, it's a club. It's a collection of subsets. If x, y are elements of x, these are points, and x not equal to y implies that there is at least one index, I, such that distance of AI to X is different from distance of AI to Y. Oh, I forgot to mention, it was usually those lots of papers which people wrote usually start with application. The gloriously politically correct application. Lots of things will be mentioned in the beginning of those papers, such as geographic positioning system, robotic navigation, whatnot. But I don't think any of these people who do this research actually have anything to do with those applications. Because if you are really going to claim application, you have to have a patent in the company where robotic navigation company, they have a patent, they have your name in their hardware. Then you really claim that your thing is applied. Otherwise, this is going to be, when it goes to research and application, it goes to the top. You look at that. If this one has none, but that one has such a patent, then that is definitely you. The same topic. He will be understood as applied. So it is not very good idea to be politically correct. Current American president is definitely one good example of one who is not politically completely incorrect. I like it. So this is what it means. So if this collection of sets can distinguish different points, that is what you're saying. If the points are different, then there must be at least one of them, the distance is different. Then we call this collection of sets resolves the space. Then we use this script font which collects these i's and where I is an I. Resolves. Metrically resolves X. And the minimum cardinality of such a set, if it is a set. If it is a set, this script is a set means that elements are not repeated. Order doesn't matter. If it is curly bracket. So if it is a set, then we take the cardinality of that set, which is essentially is equal to the cardinality of I, because when different i's are different, that is different as well because of the curly bracket. So this is actually the injective mapping from I to the A, which means that if the minimum cardinality delta, which metric dimension people use the ordinary metric dimension as beta, and the partition dimension as beta sub p. This I accept. And this is because the new definition is a delta, which is min resolves this is equal to, because what I just said, this is equal to this. Here, by putting the curly bracket outside, we only are implicitly implying that these are different sets. We never said anything about these sets are disjoint or intersecting. We didn't say. So this is my definition of metric dimension. Not published. I think it's published just now. And nothing has been done about delta yet. So we want to see examples. Examples are coming from top to bottom. Top means we look at the general things first. After that, we look at the specific things. Not like those previous, we start with very specific graphs and then say we prove the Jahangir graph has metric dimension, so on, so on. That is not a good idea. Of course, it's a good idea for teaching if you start from specific to general. And we are going to look at the general things first. Example 1. If each set is single point, then we have beta, isn't it? That is what the metric dimension is defined for graph, finite undirected single graph. So if every AI has only one point in it, has exactly one point in it, then delta is equal to beta. Here we're talking about metric spaces. So this delta was only done for graphs. So we are now, when saying this delta for graph, finite undirected single graph is delta for finite undirected single graphs. If X is a finite undirected single graph, we're going to define it immediately today. Undirected single, maybe connected graph. In which case, this now reduces down to beta, if each AI is a single point. Secondly, the partition dimension, beta sub p. If this curly, this script I, A, is a partition, of X, then, and X is a finite undirected single graph, because the partition dimension is only done for finite undirected single graphs and some infinite graphs. So if X is the graph, then we have delta is equal to beta sub. This is clear, right? Because that's how we take a partition of the vertex set of the graph. Partition means it's a non-empty subset. Each member is a non-empty subset. No two members intersect, and the union is the whole vertex set. Then in this definition, the results and minimum cardinality of the partition is called the partition dimension. So these are the general. I think I can probably boast to say that something like 500 papers are published in this, and something like 50 papers are published in this. Because of the famous people who came to this ASSMS, and then they got almost half of the students doing the same topic. And I actually was in their discussion in the seminar all the time. That is why I started learning this as well. I made a comment to Professor Tomescu from Romania. And he didn't get offended. Because I said, after these, all students are presenting this dimension, metric dimension of finite undirected single graphs of a certain type. I said, Professor Tomescu, are we not missing the point? I said. And he was not offended. Tomescu was never offended. And he actually understood what I was doing. Because graphs are only a special type of metric spaces, this concept must be done for metric spaces. First, it is their home. It is the metric spaces are the homes of this concept. We shouldn't really focus on only finite analytic single graphs. Focus, this is really focus. Focus on finite analytic single graphs. So this was I achieved with some of my co-authors something in that respect, because we went back to the metric spaces and did very good things. Very good things. Submitted, immediately accepted by non-graph theory theorists, of course. The graph theory people cannot accept it because probably they can't understand it. I don't know. So this is one generalization, and nothing has been done about this yet. Even if you have the union of these sets, union of the number of script A is a proper subset of X. Even that generality is not counted. Nothing has been done in this generality, even for metric, even for graphs. So even for graphs, this is interesting. So if you consider a graph, not just finite analytic simple graphs of certain type, consider any graph which we are going to define just right now. Consider any graph, and then if you take for example, the graph, you need to assume that it has lots of circuits in it. Then you take a set of circuits, and their vertex set is collected as AI. Then what happens? Nothing is written yet. So if you even do some experiment, this is publishable. So this is the last bit of, yes. And what are known about data? This data for general metrics. I'll just use this part. Example 2. With just data, which is a metric dimension of a metric space, not just graphs. The metric dimension means that these sets are all single points. Rn was known. Let me list it here. No, it was an exercise question in Blumenthal's monograph, which I'm always talking about this Blumenthal's monograph. You should check it out. It is an exercise question in that was proved that this has beta equal to n plus 1. And in my paper with this is Blumenthal. In 1953 was very good. Much longer earlier than Hararian later started considering this for graphs. And then we know that this, I will do an particular example of this now. This Sn, Riemann space of dimension n, it is also n plus 1 with root. Hyperbolic space of dimension n, it is also n plus 1. You see that we are completely out of graph theory. And these two are done in paper by me and myself and Hilden. In 2012, that is where I started considering this kind of thing. The story was very interesting because he was visiting our university and giving, he's a very good, he wrote 5 books in complex analysis and so on, and geometry. Some of them were in Springer series. So he knows about 5 different ways of, the story was very, very beautiful. 5 different ways of treating the complex valued function of one complex variable. And he presented to us at least 3 of them in a very general seminar talk at University of the Witwatersrand, and by the time I was there. And the only one who was asking questions all the time was me. There were something like 20, 30 people. I was always interrupting and asking questions, and he never minded, he didn't get off it. At the end, when he finished the talk, he asked me now a question. What do you do? I said, I do nothing. I am doing very good. But you must be doing something, he said. Yes, I'm doing something. I have proved this is a Bloom's result, and then I have proved that this is a proof that. I don't know about that one. He didn't say anything and went back, and second day, beautifully written manuscript. Not only with he proved HN is also N+1, but also Riemann services. Riemann services is a Riemann service. And we published the paper. Then beta x is equal to 3, which is just 2 plus 1. 2 is the Lebesgue dimension. And the proof of this was non-trivial. Those are actually covered by this. And this was done with a very beautiful theorem applied, called uniformization theorem. The complex value function of one complex variable. Many people thought that not everything has been done, but in 1960, the uniformization theorem was proved by someone, which determined all the Riemann surfaces using the discrete group of isometry. So the Riemann surfaces are all known. Therefore, using that theorem, we can prove and lift it's quotiented by discrete group of action, isometries. So in that quotient, we know exactly what's happening. And then we lift it up. You have only finitely many points for each point. Each point is mapped to from finitely many points from the Riemann sphere. And then it was easy to deduce that this is true. Not only so, we did lots of other things. Every open subset of a fine Euclidean, of a fine space, open subset with interior. So there's at least one interior point. We prove that it is n+1 in Rn, in a fine series of images. And we also completely determine which metric spaces has metric dimension exactly 1. So that paper is from 2021. If you are interested, it's not difficult to read, so just find it. I will not mention more than this in this whole course. Now,
Sir,
definition of a bicycle.
sir, I have a question.
Sorry?
From here, in defining the definition of dimension, you are using the cardinality of capital I, that is a subset of the natural number. But you can say that AI is relative to cardinality of I. So I think this I should be replaced to the AI's a similar result.
Is it replaced by X?
This cardinality of I here from AI's.
Yeah.
Yes.
Not AI, this
Nee, above.
Yeah, this.
Yes.
This I is fine.
Finite.
Yeah. This is better because, well, I forgot to mention one thing. If I is finite, then you have finite dimension. Finite metric dimension. So that we didn't say. And it happens that you see these are all complete spaces of continuum cardinality, but their dimension is finite. Their Lebesgue dimension is n, and their metric dimension is n+1. I regard this kind of result as beautiful, and the proof is not suffering. Nowadays, the suffering proof is really looked up so much. Even if you have an easy proof, you should convert your proof into a suffering proof, so that you really went to the war and then you have lots of wound on all on your body, and then you are killed. If the good fighter who killed most enemy but never got wounded, even not a drop of blood on his skin from his victims, then he is not a hero today. You have to really get wounded, nearly dead, and then you are here. So, I don't know. So beauty means that you really do something without much effort. Something quite deep, but not much. The proof is actually easy. And one more concept in this. something called bisector. So we pick still AB. So my course author and myself use B there, but because we're going to use AB as subsets, B is also inside, we should really change it into this one. It's better because the word bisector was a wrong one actually. Equidistant set, so it starts with E, no problem. Equidistant set means corresponding to two subsets A, B is given by X in X. Is X any metric space? One of those. Oh, I also have to do S2. So that rho AX is equal to rho BX. We collect all points of the space which has equidistant to A and B into this set. Here, I always want to tease my young audience. What if A and B are equal? What do you get? What do we have? You have to answer quickly. This is the whole space, isn't it? It's the whole space because you're looking at
everything is
going to the same distance. And that distance is only one there, so it doesn't matter which. So this implies that EAB is X. I want to illustrate something here. Let us be careful. I want to treat it also. Suppose that we have a Euclidean plane. This is A. With points inside included. And we have another one B. What does the equidistant set E look like? So if you have something like flat like here, it has to pass through, contain this point. Could be it goes somewhere there, I mean it could go something like that. Something like that. So this is your EAD. Of course it's not precise. We are at every point, we are looking at this distance is equal to that distance. And I have asked for compass and ruler, but I didn't bring. If anyone can lend me a shoelace, I can do that. Euclid was Euclidean elements, 13 books, the first 5 books. He was constructing everything using two tools, two very simple tools, compass and ruler, we call it today. For example, if you have 2 points in the Euclidean plane, he was Euclidean plane all the time. You can actually find its perpendicular bisector by the compass and ruler only. The ruler is unmarked. The compass can measure any distance and replicate it. Now let us have a look at n equal to 2. What happens to S2? I should really, now I have graphic display, but it's fine. n equal to 2. And consider S2. S2 is the Riemann scale. Everybody knows about it. It has an equation even. And using the distance to define bisector, it was Hilbert. Took 2,000 years to. Euclid was this Euclidean distance x minus y. Names of the vector x minus y. In our terminology, it's U2. So let me try to, I'm not good at hand drawing things. I can draw these things very nicely with computer. There is a center, and we can even assume that the radius is 1. So it's x squared plus y squared plus z squared is 1. All those x, y, z in R3. This is the Riemann sphere. What is the bisector like if you take any 2 points on this? So let us take 2 points. More generic. This is your A, small a. And let us take on this side, this hemisphere. This is your small b. We assume that it's on this hemisphere, on the side. Now, by Euclidean axiom, center A, B, 3 points, if A is not equal to B, and A, B are not equal to the center because they are assumed to be on in the space. In the space means on the S2. So neither A nor B is equal to that. If A, B are not equal, then we have 3 distinct points in space. By Euclidean axiom, there is a unique plane going through it, right? There is a unique plane containing it that intersects this sphere in a what? In a great circle. So that great circle would look like this. I have nice drawings in my slides. This is the plane intersecting plane through those 3 points. This point, that point, and that point. And this intersects the space in great circle. Now, how many points can resolve this metric space? Can one point resolve? No, it's very easy to understand that if we take any point, any circle on the Riemann sphere has all the same points, different points, all these imaginary different ones have the same distance to that point. Therefore, 1 is not possible. This means that it is a piece 2. So beta is a piece 2. Can it be 2? Let us take these 2 points. Then what happens? There is a middle point of this segment, this arc, and then through that middle point, there is a unique great circle passing through it. Wrong. That is supposed to be dashed. This one is whether it is this one, sorry. Now I'm messing up the picture because I have nice drawings in this one, this point. On this great circle, if you take this point, these 2 distances are the arc distances are the same, then that these from this point, if these are the same, from this point for those 2 distances are the same. So these 2 points as a set doesn't distinguish these 2 infinitely many points. That doesn't distinguish, which means beta is not equal to 2. Beta is at least 3. Is 3 enough? So let us erase this great circle. Oh no, we should have erased the red one. So this great circle is red. It is. Is 3 enough to resolve this? So let us take these 2. These 2 cannot resolve. So as soon as you start taking another one here, then it will resolve. So only points which cannot be resolved by these 2 are on that great circle, right? But if you take one point here, its distance, only the equidistance is this way and that way equal, but in that case, those distances are different. So 3 points will resolve, which means beta is not both 3. This implies that beta is 2, 3. I will display beautiful drawings later on. That was the idea for Sn, the Riemann space of Lebesgue dimension n. Of course, as soon as we do this using uniformization theorem, these are all special cases, by the way. Oh, when n is equal to 2. But when n is not equal to 2, they are not special cases of that. This is as much as I wanted to. This is the end of the second batch of slides. I hope I'm right, because there might be something missing or something additional. I don't know. Now we're going to enter the third batch of slides. Any questions or discussions in this? You need to really know that lots of things can be done with this concept. Even without making reference to any application. Comments or questions, I really welcome. If you want to do something new as well. So the next batch of slides is graphs. I have to tell Dr. Ali Raza that what contents I am covering. I have to remember dimensional graphs. Dimensional graphs. The next batch is graphs. I forgot which graph. I want to draw a few graphs and ask you to. Of course, many of you know what the definition of a graph is in all those books in the library, which I'm saying that you shouldn't read those. You should not. Because we're going to form yourselves, a much better definition today. And this is just recently published, because I have hung this paper on archive 20 years ago, and then around 2005, and then no response. So somebody wanted the paper, and I gave, and it is published just recently. So we are going to, first, before we draw graphs, we're going to give some common definition about sets. So let B be a set. Common notations. So we use for our natural number, V to the R to denote V cross V cross V R. So R for the Cartesian product of set V. And then we use this concise symbol V, choose R, to denote all R subsets of V. And we usually denote by 2 to the V, all subsets of V. The set of all subsets. And by D sub V, the diagonal of binary equation on V. And by, if E is a binary relation on V, this is what we mean by binary relation, right? You should really know this. Just a subset of any subset of V cross V is called the binary relation on V. Then we define the symmetric completion. S of B to be E union Yx if xy is in E. If it is already there, because we are using curly bracket, it's fine, we don't need to add. If it is not there, we are adding into if this is x is related to y in binary relation E, then y is, we regard y as related to x as well, which means this is the symmetric completion. And
For diagonal, we want our coordinates are only two coordinates.
all of them. Two coordinates, yes. It's a diagonal for binary. Of course, we have a similar one for any fold. This is essentially we're trying to subtract that set out. So there's a P sub S mapping, small p. This maps from symmetric completion of S cross X minus the diagonal, D cross D. Minus the diagonal of D. We choose 2. This mapping forgets order. We usually say using Professor McLean's word, forgets order. Of ordered K. So ordered pairs are mapped to subsets of cardinality too. Because we could take out the diagonal as well, so there cannot be anything like curly bracket AA or curly bracket just A ordered K.
How you are defining this S of V? Where you said this is E union something and that looks again E.
Yes, E is already given.
Yeah. Then
If Yx is not in E, then we introduce Yx if Xy is in E. So if this way the relation is there, if it is not, the other way is not there, then we add that one in, which means the relation becomes symmetric. So it's called the symmetric completion. Symmetric completion. Discrete mathematics has this all very, very well done, lots of exercises. Of E. Now I'm going to draw a few graphs. I ask you to work at least 5 minutes, 3 minutes to at least say a definition which covers all of them. All graphs which are, for which these graphs are typical examples. So, and one thing I don't like is I don't like verbal description. I want a precise definition. All the books, including the famous Hebrew books, they never have this in this way. Because they are only concentrated, focusing on a special family. So, they are focusing on special family, even if they are not optical lens. People ask me, what are you focusing on? I said nothing. Because I am not a lens. If you focus, it's a microscope, you're focusing it is lens, not human beings. So when people ask me, what are you focusing on, I don't use this word usually. Now I've used 5 times already. So there are 5 graphs I'm going to draw, doesn't matter how it looks. These are metric spaces of course, and I'm going to vigorously introduce graphs as well because some questions can be done for graphs as metric spaces, which could be easier than others. There is arrow here, these are arrows. There is no arrow here. There is an arrow here. There is no arrow here. And there is no arrow there. 0, 1, 2, 3, 1, 2, goes on. Fourth graph. I said 5, but it is 4. I'm not going to count it. 4 is enough. So look at them nicely, just like looking at your most loved one or longest friend, and give me a simple, precise definition, and I don't accept verbal description. And then if you can manage to come to my definition, it will be nice. But this paper was hung 20 years ago in Archive, and this year it is published. You can work on it in your papers because you need to probably name something.
If you could repeat the question.
We are given 4 graphs here. The condition is that we are given 4 graphs here. Please write down the definition of a graph which covers all of these. Very special examples.
Separate definition for each graph or the
No, definition of a graph
which covers
which covers family containing, infinite family containing any one of these. Because these are, let me point out, these two have finitely many vertices. The rounded bits are called vertices. And finitely many edges. This one is simple, that one is not simple. And this one is not only not simple, there are edges which are not undirected and edges which are directed, loops which are undirected, loops which are not directed, directed and directed. This is infinite, that is infinite, these are simple. You need to have a definition which, as soon as you see any one of these, you can write down using your definition, oh, that is it. Your definition must help you instead of this verbal description in 20 books in our library on graph theory. Any one of them, there's no precise definition, it's all verbal description. That verbal description doesn't help you to understand and use it especially when you want to carry out what is my criterion for this to be this and that. Your definition should help you on that. It's not, we're just showing people abstract concepts. We're serving our own self to facilitate our own thinking. That is our objective. Any suggestions?
collection of set of vertices and set of edges.
Yeah, this is verbal description.
It's your
Yeah, there are sets involved, yes. For example, I'm familiar with all those graph theory books because I used probably any one of them as a lecture notes sometimes. On this definition is that, oh, it's a finite set of called vertices and finite set called edges, and there's an incidence function given, which clarifies on which edge has two ends, which two vertices, or one end, which vertices. This is verbal description. On the other hand, these two books has given two sets, and then used ordered pairs. Ordered pairs is only or unordered pairs. Unordered pairs only these kind of edges, and you cannot really, if it is pairs, then you cannot really accommodate these two. They are not pairs; they are just one vertex, an edge. An edge whose end is one vertex, And in one case it's guaranteed, in the other case it's not. And lots of other books, especially Wilson's book, it's completely verbal. When you, a new student, when they read it, what is the feeling I would have, when I'm a new student, when I read it, only way I can, and I can try to apply this is, I have to memorize it. I don't want to memorize anything for such a simple definition.